Okay, well, good afternoon, everyone. Welcome to the UCCS Speaker Series. I'm Richard Kravitz, Director here at UCCS, and it's a pleasure to have you with us. This is the fifth talk of our academic year, which continues with our 2020-21 theme of emerging from the pandemic, promoting health and prosperity for all Californians in the wake of COVID-19. Just a brief word about UCCS as always. If you're new to us, I want to extend a special welcome. We're the Sacramento outpost of the University of California. We're one center with two goals, educating young people in the process of leadership and how politics and policy work in the state of California, and also sharing knowledge for the purpose of promoting and providing support to better public policy in the state. And of course, what we share and how we share it depends on you. We rely on you, our policy audience, to let us know what is needed and meaningful to you. So please do correspond with us if you have ideas, things that we ought to be sharing with you that we're not. So now to today's topic, creating a sustainable battery framework for a climate neutral future. If we're to get a handle on climate change, we're going to need to rely more on wind, solar, and tides. But the problem is, of course, that winds don't always blow, the sun doesn't always shine, and tides aren't always shifting. So we need to store that energy cheaply, safely, and effectively. For this, batteries are a critical technology, and UC has been a leader in the development of battery technology for many years. And Dr. Miri Ozkan has been a leader in this area at UC. Dr. Ozkan is professor of electrical and computer engineering at UC Riverside. As you can read in her bio, she's the recipient of many honors and awards, including election to the National Academy of Inventors and selection as the John J. Guerrera Engineering Educator of the Year. She runs a very large and productive lab at UC Riverside that incorporates some 15 graduate students working on problems like advanced battery technologies, supercapacitors, and two-dimensional van der Waal materials, which I understand are thin membranes that are very useful in the electronics industry. As is typical for us, our format for questions is that we'll reserve them to the end, where you can press the raise hand icon and we'll call on you, or type your question into the Q&A section of Zoom. So now, without further ado, please join me in welcoming Professor Miri Ozkan. Professor.
Thank you very much, Richard. Before I get started, I really would like to thank Richard, Cindy, and Sandra for this nice invitation, and thank you for joining and listening about how we can create a sustainable battery framework for moving forward to have a climate neutral future. And one of my hobbies is making cartoons, and these are my own cartoons, and throughout my presentations, you will be seeing some of those. So I am going to get started with the current status in carbon emissions today. And if we look at the reported values, anywhere in the average of nearly 420 parts per million, which is about like 50% higher than the Industrial Revolution levels, which was back in there in time, it's like 280 parts per million. And this actually resulted in, again, based on the recent reports in 2020, an estimated 1.27 degrees Celsius increase in the average surface temperature on Earth. So what does this mean, increasing the surface temperature? So we are seeing the effects already. The severe drought, severe rain, and severe hurricanes, and all these effects we are already experiencing, unfortunately, at various parts of the world. So moving forward, what can we do? Probably we can move towards the electrification of carbon emission sources. And one of them is electric, basically cars, vehicles that we are driving. And also trying to use not fossil fuel based electricity, but green basically electricity. So that's why what you see here, like 4 different applications, immediate applications of lithium-ion batteries today: consumer electronics, aerospace applications, stationary energy storage, and electrical vehicles. And as you can tell from all is that they require different power densities, different capacities, and based on the application. So we need to pretty much like develop a customized the battery system for the application. And it has been also found out that the life cycle greenhouse gas emission of electrical vehicles are around 50% of the internal combustion engine cars on average. So if we have an EV, so we can potentially reduce the carbon emission 50% compared to the combustion cars. And this can be even improved further with the advanced technologies, and this can even add another 25% reduction in the carbon emissions. For those of you not familiar with how batteries do work, and this slide is for them, and you see this internally, how a lithium-ion battery is structured. On the left, you see a positive electrode, which is called cathode, and the negative electrode, which is called anode. And the traditional lithium-ion batteries, they have graphite layer structure on the anode side and the lithium cobalt oxide on the cathode side. And during the discharge, these green basically balls that you see representing the lithium ions, the lithium ions leave the graphite and then they intercalate into the lithium cobalt oxide. And during the charging, and they move away from the cathode, lithium cobalt oxide, and go back to graphite. So this actually circulation happens in every cycle. And if you look at from the performance perspective, the theoretical capacity of graphite is 372 milliamps hour per gram. And for the lithium cobalt oxide, it's 270 milliamps hour per gram. And in this scenario, so we see that it is limited by the cathode. So cathode is the limiting factor for the performance of the batteries. Even though the theoretical capacity is 270, today with this lithium cobalt oxide cathodes, we only achieve around 140 milliamp hour per gram in the real applications because of the instability issues and also simply losing the layered structure of the lithium cobalt oxide during charging and discharging. So regardless, for the next generation lithium ions, we need far more capacity than this. And this is why many people worldwide is working on developing new, better battery technologies. If you look at the global, I'm trying to move my, cool. All right, so this is better here. And if we look into the global battery demand and comparison from today, 2021, and all the way to 2030, you see a huge increase. And this increase and the different colors representing different sectors. And in transportation, the expected demand is 9 times. but on stationary storage is about 5 times, and consumer electronics is about 2 times. So this tells us that there is a huge demand in the battery capacity. So we need to somehow produce this and either purchase from whoever is producing, or internally in US, we would like to produce this. And today in US, battery production capacity is basically targeted to increase up to 80 gigawatt hour per per year by 2023, just to kind of like make sure that we have enough batteries for various applications, various sectors, and mainly for the transportation and EV vehicles. Okay. And let's look at the annual battery and battery pack suppliers to US. And on the left, it shows the battery cell and supplies coming into US, and the battery packs coming into US. And the gray dark color here representing the US. So the majority of the packs and the battery cells are produced within US, which is great. And beyond the US, South Korea and Japan are the major countries supplying batteries to the US market. And about 70% of the battery cells and almost 90% of the battery packs produced in US in 2020 is coming from the single supplier, which is Tesla Panasonic. And let's look at this globally. So who is the leader in terms of battery capacity production? And CATL is a Chinese-based company, actually is about like 33% of the market share. And LG, Panasonic, and BYD are the next three that follows. And one thing to notice is that the CATL and BYD, between the two, 40% of the today's battery market share is from China. So the majority is coming from China. And contemporary Amprex technology, which is short in CATL, actually they have risen in less than 10 years. So this is a huge, I guess, success. And I am going to use them as an example and then go through what type of critical decisions have been made to make them successful, both from the government point of view and also from the company perspective. So here's the success story of CATL. And again, they are about 50% of the China's market share and 33% of the global share. And their valuation is around 186 billion within just 10 years. And they supply to Tesla, Porsche, Hyundai, Honda, BMW, Toyota, Volkswagen, Volvo, and others. And so you can see that they are the main suppliers to major car makers. And CATL's CEO, Zheng Yang, actually was born in a poor village in 1968 during the Chinese Cultural Revolution. And now he is worth almost as much as Alibaba's founder, Jack Ma. And they have already started making connections with Tesla. So Tesla became one of their big customer as well. So continuing on the success story of CATL, I think we should pay attention to the graph here. It does show that how the EV sales did change from country to country over the years. And as you can see, in China, it just doubled from 2017 to 2018. And United States is here, and Europe is there, and the rest of the world is here. And this is a huge factor in the success of CATL, because this is a country, basically government-based subsidy that actually made CATL successful. And CATL grew rapidly, and because of these government policies and banning of foreign companies is one factor. And they passed both LG and Samsung in consumer electronics, because Chinese government also helped the battery manufacturers. They acquired lithium, nickel, and rare earth materials to the manufacturers. And this actually helps in terms of the lowering the manufacturing cost to the company. And one of the important, decisions was CATL produced a prismatic type of cells, and then they are much safer. So their names are not part of the like fire newses that you have seen even for Tesla, Panasonic, and Samsung, and others. And lithium iron phosphate is the technology that the CATL is using. They don't use cobalt, nickel, manganese, which are expensive minerals, and that lowered their cost even further. And using the lithium iron phosphate, Tesla can save about $600 to $1,200 per car if they run the Tesla cars with the LFP batteries. And another critical decision was CATL moved from the cell technology to pack technology, and this increased the density by about 10 to 15% and improved the volume utilization, again, about 15 to 20%. And this also reduced the parts needed by about 40%. So this was I think, a great move. And now Tesla is trying to adapt this, and they are learning and talking with CATL. And now recently they start moving into sodium batteries, moving away from the lithium, thinking that, you know, a shortage in lithium, can happen. And one of the important factors is also that CATL, almost about 5,000 of their staff are working on R&D. And they spend 11% of their revenue on their R&D. So this is quite important. And they already have foreseen this, the potential shortage in the minerals like cobalt and lithium. And they already announced a $5 billion battery recycling facilities to retrieve these expensive, basically, elements. And some subsidies that we need to mention to increase the competitiveness, starting from China, they spend about 58 billion on subsidies through 2018, and they keep EV prices low. And they gave exempt vehicle purchase tax, and they also applied, gave some subsidy to the manufacturing costs, and some additional subsidies to fuel its electrical vehicle boom. And China new energy vehicle mandate has set a quota actually for zero emission vehicles that automakers must sell and provide credit targets. EVs must account for about 3 to 4% of the Chinese automaker production. And then China now provides performance-based subsidies as well. And many provincial and local governments do also promote EV charging. And they have one nationwide fast charging standard that they applied. And they also, government helped to build this infrastructure for charging stations. And this makes it, very attractive for people owning EVs and people making EVs as well. And then the policies to study from the Chinese government, multi-layer planning with respect with the EV charging infrastructure, I think is something to pay attention. And if you look at in Europe, in Norway, they lead and they provide tax exemptions also, and the purchase and import tax and 25% VAT, annual road tax, and 50% road and ferry tolls, and 50% parking fees are some of the subsidies that they provide to EV owners. And other European Union mandates, starting in year 2025 and 2030, a new regulation, EU fleet-wide carbon dioxide emission targets are set, and these are very strict, and which are defined as a percentage reduction from the 2021 starting point. And they also offer tax reduction and exemptions. And Clean Vehicle Directive also encourages use of electric buses for public transportation. And the Energy Performance Directive is another one here. And California, just comparison to US and in California, since we're in California, I just took mostly from the California. Auto manufacturers are required to produce a number of electrical vehicles and plug-in hybrids each year. And based on the total number of cars sold in California by the manufacturers. And so this is just to encourage to produce and sell more EVs simply. And the requirements are in terms of percent credits, ranging from 4.5%, which was the value in 2018. And then the targeted value is about 22% in 2025. And the IRS tax credit, about 7,500 per EV purchase, and up to 200,000 EVs sold. Colorado, Louisiana, Maryland, and New York, they give additional tax credits. And then North Carolina and Colombia, they apply inspection exemptions. And free access to the carpool lane and parking in Arizona, Hawaii, and California are some of the subsidies are provided. In Alabama, actually, they charge annual EV additional ownership fees. And this is just to offset the cost of building the infrastructure for mainly charging. The battery rush and the competitiveness is quite important for the security of the country. And now in US, there is a big rush in making and building more battery plants. And what you see here on the top, Tesla, one in Nevada and in California, Fremont, and Envision in Tennessee, LG in Michigan, and SK in Georgia. So they are all built basically battery plants. And the other key players are decided to move out of their countries, also become international. And they started building the plants internationally as well. So Panasonic is building a plant for Tesla, and GM and LG building in Ohio, and Samsung building in Hungary, and CATL is in Germany, and Volkswagen in Germany and Sweden, and SK Innovation building one in Georgia. So the battery companies decided to be international. I think that is a very smart move because this is a global demand, and at the same time, the transportation issues that everybody is facing today, is a main roadblock to prevent that building their plants, battery plants overseas. I think it's a smart move. Pros and cons of different lithium-ion technologies are summarized here. So this is like 5 different types of lithium-ion battery technologies, and they are compared based on the cost, specific energy, safety, lifespan, and the performance. And Tesla chose to use NTA, which is nickel, cobalt, aluminum based. And because the cost is low, and then it gives a high specific energy for the performance, but has some issues with safety. And NMC is another most common one used by Kia, Hyundai, BMW, and Mercedes-Benz. And with the high specific energy, but slightly higher cost, but the safety is much better compared to Tesla's. And the CATL is using lithium iron phosphate. And so even though the specific energy is slightly less, the safety, lifespan, and the cost is very high as compared to other technologies. Let's look at the minerals. So how the minerals distribution look like in different types of batteries. And here is NMC, here is NCA, here is LFP and LMO. And the color codes are showing, how much of which element is being used. The orange is representing nickel, the gray graphite, and then and I guess this is maybe the orange, the cobalt. And NMC, which is Chevy and BMW, are heavily on the nickel, graphite, and cobalt. And same as the Tesla, so nickel, graphite, and cobalt. And CATL is free of cobalt and nickel, mainly is graphite. And so as the Nissan, so that's what they use. So if EV is made of NMC 532 battery packs, and only one car contains around 8 kilograms of lithium, 35 kilograms of nickel, 20 kilograms of manganese, and 14 kilograms of cobalt. So imagine that this is only one car. And then we know what's the projected number of EVs. And this is going to be a huge demand on these minerals. And indeed, the projection to 2040 shows that, so this is the case for lithium, and this is the demand growing over 40 times. And for graphite, cobalt, and nickel, this is expected about like 20 to 25 times because of the rush in EVs. So let's compare the electrical vehicles to conventional cars in terms of the mineral needs. And as you can see on the top is the electrical car mineral distribution versus conventional car. And the electrical car requires 6 times the mineral inputs than the conventional cars. And if we look at what type of minerals these are, so the orange shows the graphite, and the yellow is cobalt, and the green is manganese, and the light green is nickel, and the blue is copper. So these are the major components that actually is the makeup of the battery. So the battery pretty much like determines the mineral needs of the EV overall. So where do these minerals come from? So this is very important. And if we look at the lithium, mainly from Australia, about 60%, these are all global, basically supplies. And from Chile is about 20, and about 9% from China, and Argentina is about 7%. So this tells us that we don't actually used to have lithium sources. So the import and trade policies need to be polished because of the huge demand that US is going to have. But recently, luckily, in Rio Tinto, an Anglo-Australian conglomerate announced that in 2019, they found a large lithium source in California, which is great. And now they are thinking that lithium has generally not faced a political instability risk because of this finding. How about the other minerals, other key minerals making batteries, the cobalt, graphite, and nickel? And the cobalt, because the Congo's political instability, it's a major issue. And the companies are responding to this by eliminating or reducing the amount of cobalt used in their batteries. And the graphite, obtaining graphite EV does not currently pose difficult geophysical obstacles. But still, because mainly China, Japan, and US can produce them artificially. And the nickel, the largest competing demand for nickel is used in stainless steel manufacturing. And if you look at the sources that are coming, these are all from overseas, not from US, cobalt, graphite, and nickel mostly. So that's why I think the import and trade policies need to be polished well in order to eliminate any shortages in mineral supply for battery makers, in this case, mainly Tesla. So in UCR, jointly with Professor Cengiz Ozkan, we've been working on lithium-ion batteries. So these photos are taken from our battery lab in UCR, and it's well furnished, and we can test both coin cells, and we can test also the any type of packs, and with the larger size, different formats of batteries as well. And with the environmental chambers that we have, so we can test it under a different environment too. So one of the things we wanted to look at is using alternative materials like waste or, or renewable sources to kind of like looking ahead of time that there might be shortages of some minerals, and we want to bring an alternative material supply to make batteries. And one of them is the plastics, and 79% of the plastic today are accumulated in landfills. And then, so that's why only about 9% are being recycled. So we said that, okay, let's see if we can get one of these plastic bottles from landfill and then process that and convert that into a material useful for making batteries. So the video that I am going to show after the slide is simply going to show how we are making this. And one note is that the plastic bottle, the estimated decomposition is around 450 years. So if one of us, drinks a bottled water and then just puts in the environment, it's gonna be there for about 4 to 5 generations. And the glass bottle is undetermined, so probably it's there for good. And so that's why we said, okay, let's look into both glass bottle waste and also plastic waste and see if we can convert them into a material that we can use making lithium-ion batteries. So 2 movies back to back will show how we did this. So the first one here is showing the plastics. And it just shows like some of the selections that you can have. And these are like very common plastics, PETs. And so as you see, the student is cutting a piece and dissolving the plastic And after that, so we are using an injector. As you see, we created a cloth. And this is the high resolution image of that cloth fibers. And this is even like atomic scale of representation. And now they are building a battery just made of this plastic. And we made a supercapacitor, and also we made a lithium-ion battery. As you see, it works. It just turned on a light. So this is one of the testers that we are using and testing our batteries that we are making, which are being used also by the battery makers. All right. So the next movie is going to show you the glass waste. And it just shows like the landfills are full of that. We took one of the Starbucks, basically coffee glass, and crashed it and turned that into a material that we can use, a nanosilicon, and super high, porous. And we are making the battery right now after processing. And it just shows how we are building. And now it's under the tester. And it's just showing that we indeed made batteries out of these. Just to give you a list, what type of batteries we have made, and using this renewable and sustainable sources. We made batteries out of portobello mushrooms, and this helped to save about 15% of the cost. And then we used beach sand, and we took sand from the beach, literally, and then turned that into a porous silicon, and that saved about like 30% of the cost of battery making. You just saw the video about the glass waste bottle, and that also saves about 30% of the cost. And they actually performed very well. So these are all documented under our publications, and we have patents, about 29 issued patents on these. And additionally, carbon-coated silicon nanofiber. So this also saved us about 25% the cost, and with the lightness, about 6% weight saving. And diatomite is one of the fossils that many people are familiar. So we use that as a source of silicon, and then that also helped to save the cost. And plastic waste bottle, you watched the video, also was another sustainable source. And we did also demonstrated a larger scale, not the coin cell scale, but 15 layers of a pouch, which actually what you have in your cell phone. And then compared ourselves with other competitions out there. And our cost was about 30% less. And then the performance, the capacity, the storage capacity was around 33% more. And we have patents on those as well. And because of this, again, potential mineral shortages that we are expecting, so we wanted to go to the elimination method and not to use some of the components that are part of the current traditional batteries, for example, without copper, without binder. And then, so that's how we developed these two technologies also, using nickel oxide nanofiber cloth anodes, and these are binderless and freestanding without copper, and nickel oxide nanowire foam, again, template free and binderless. And so these are some of the technologies we used. And more recently, there is a trend to move towards, cobalt-free, as I mentioned, because of the cost, cobalt-free or low cobalt type of the cathodes. And this kind of like moving and replacing cobalt with nickel. So making nickel rich cathodes, and they are like very high performance cathodes. And there are standing issues with that. And there is a very strong acid formed during the cycling, hydrofluoric acid, and that decomposes the electrode and then cause this electrode metals to dissolve into the electrolyte. And that creates lots of structural issues and damages. And we try to develop some of the prevention coatings on this nano layer of, in this case, manganese fluoride is one of the films that we coated. It just shows that the manganese, fluoride is there, and we used standard NMC, nickel, manganese, cobalt type of cathodes, and it just shows that very nicely covered, uniformly covered surface, and then we are doing, both fast charging and like a standard charging just to see how stable these coatings are. And the next generation is aluminum solid state batteries, all solid state batteries. And here the liquid electrolyte is moved out of the picture, and the electrolyte is solid, and which gives us inflammable and safer environment. And we are looking into the interface issues, which there are plenty, and the high interfacial resistances, thermal instabilities, mechanical instability. So these are all good challenges that we are working on. And the future of batteries moving towards the solid state batteries and away from the traditional liquid electrolyte for the safety purposes mainly. And Japan's Toyota, currently they are struggling with what they are working on and their short surface life of these solid state batteries, and they are working very hard on it. And then here, Germany, Volkswagen is working with Bill Gates-backed QuantumScape, and they are claiming that in 2024, they will have Volkswagens and EVs running with the solid state batteries. And other VW also claims that they have 30% more range and then charging 80% capacity only in 12 minutes of these stable solid states. And other companies, the Fiat and France Passa, and they are also working on this. Ford Motors is also working in the solid state batteries now. And the Hyundai and Samsung SDI, they are all working on this. Only Tesla did not say anything that they want to use solid state batteries in their cars. And besides the solid state batteries as a future technology, another one here is the sodium, moving away from lithium because of potential limitations. And none of the beyond lithium chemistries are straightforward. There are like some challenges because of the sodium being a larger size of an ion, and then it just creates more stability issues during charging, discharging. And the lithium-ion batteries that we have today, they require, for example, the cobalt, nickel, and graphite. And these are because of the supply chain issues. That's why they are trying to move away from this. And the CATL, they just announced their first generation of sodium-ion batteries, as you see here. And they made a comparison here on the right with the sodium-ion versus the lithium-ion. So the blue, light blue, is the sodium-ion, and the other gray at the background is the lithium-ion. So they are pretty close. I mean, for the first generation, it's still doing quite well. And this, regardless, this import-export trade policies need to pay attention because of this mineral shortages, just like the chip shortages that EV makers are facing today, even Apple. So they are trying to reduce their production capacity because of the chip shortages. And similar, I think, the shortages for minerals, for these key minerals, are what we are going to observe in the future also. And from the science perspective, so we must learn how to control the metastable materials. And because all the battery minerals are working in a non-equilibrium and harsh environment, and especially at different and voltage, basically abuse, I would say. So we need to learn how to control them better and how to control the interfaces, because there are many interfaces there. And then we need to develop structural models of these interfaces and understand at the atomistic scale also what exactly is happening. And potential self-healing systems can be developed during this charging and discharging process. And either it's a sodium ion or it's a lithium ion. And because of the volume expansion and shrinkage, so there is a mechanical instability. So self-healing systems are important. And understanding, again, this multiple non-equilibrium processes in batteries is, I think, something that everyone needs to focus on, especially in academia and research institutes. With that, I think I would like to stop here. So this is another cartoon. My cartoon shows that somebody there, I think, keep looking at the watch and trying to make me stop talking. And I really appreciate it. Thank you very much for listening. And I'll be happy to answer your questions. So Richard or Cindy?
Yeah, normally Cindy would come on. She may be having a little difficulty, and she'll show up when she can. But in the meantime, this is our time for questions. And again, you can just raise your hand, and one of our staff will call on you. Or I do see there is one. It's really a comment and a request. Would it be possible to get a copy of the PowerPoint? Normally we do post those afterwards, so we probably will be able to do that this time. And they're also congratulating you on a fantastic presentation, which is something I'd like to underscore. I do wonder if you have any thoughts, any further thoughts on while we're waiting for other questions, on the security issues. Thomas Friedman wrote an interesting article today in the New York Times about the computer chip issue problem as it relates to Taiwan, and how there's limited capacity. Taiwan makes 50% of computer chips. There's a similar concentration of manufacturing in battery technologies. So exactly. What can the state or the nation, what should the state or the nation be doing about that?
I think the nation's security is definitely in stake, especially both in this battery technologies and at the same time the chip shortage. So if you look at any car maker, not just the EV, but other types of cars, they use a lot of chips for controlling the car as a sensor or in the operation. So it's like all electronic right now, all the cars. And that means that that amount of chip needs to be coming somewhere. And this was mainly from the TSMC, and the supplier is from Taiwan. And because of even they face mineral, shortages, and at the same time from the COVID and the transportation, transatlantic transportation and all that shortages, they could not make enough chips for the cars. And so that's why the most of the car makers, they reduced the amount of, their original, the numbers of cars that they plan to build, they lowered that. And the same thing, I think, will happen. We'll face this in the batteries also, because of this huge demand. And so that's why I think Tesla is making some smart moves, and they are trying to, I guess, purchase some land that is rich with lithium, for example, minerals, and they are trying to do some mining themselves to support. But the cobalt is one of the major problems, and I know that Tesla, just because of that, because mostly is coming from Congo, and they are trying to reduce the amount of cobalt they are using, and even they are moving towards cobaltless type of batteries in the next Tesla. And they are talking with CATL, because CATL's technology, lithium-iron phosphate, is free of any of these, free of nickel, free of cobalt, or any of these key minerals. So that's why Tesla is working very closely with CATL these days.
Okay, well, thank you. Thank you for that detailed response. We have like a huge number of questions in chat. We're not going to be able to get through all of them. And so what I'm thinking we might do is try to preserve these questions anonymized and get brief responses from you offline, and then post them on the website. But for now, why don't we take one live question and then one chat question? So there's a Ricard who has the hand raised. Would you please state your name and affiliation, and then your question?
Okay, I'm just going to take a few seconds just to stop the recording.
Okay.
Thank you.
That was Sandra.